Okay, very good. So welcome to the masterclass series, and this broadcast is looking at AS level chemistry for Cambridge International exams, and we're looking at paper 11 from the summer of 2014. So this is a multiple choice paper, and we're going to spend a bit more time on some questions than others because in the examiner's report there were particular questions where the examiner noticed that the majority of the students got the question wrong. So we'll be spending a bit more time on those questions where most students are making most mistakes, and other things we'll run through quite quickly. And as we go through, we'll look at a little bit of technique as well for working with these multiple choice questions as they appear in the exam. Okay. So you've got 40 questions. Let's get going. So you're given a data booklet, and you've got to have an answer here for which of these elements has 6 unpaired electrons. So you're going to be looking up in the data booklet, and you're going to be working out the electron configuration for each of these different atoms. You can do that. And what you find is that when you come to chromium, that's the argon core, and then what you find is if you write out the remaining electron configuration for chromium, it's got, I'll get that to run there, it has this electron configuration. There's stability associated with half-filled subshells. You can see that the D subshell there is half-filled, and the S subshell is half-filled. And that particular electron configuration has 1 electron in each of the D atomic orbitals and 1 electron in the S atomic orbital. And so you have there 6 unpaired electrons. And if you check the other examples here, there's various kind of distractors and things where sort of there to trip you up, but that's the one that you should have for question 1. Okay, question 2 is interesting because this is one of the ones that the examiner flagged up that most students were getting wrong, actually. And there's a couple of things. It's talking about iodine, and this iodine vapor has this particular volume at this particular temperature, and we know that's the mass of iodine in that volume. And so what you're using here is a number of different equations. You need to know that the number of moles, the amount, is the mass divided by the molar mass. Okay, that's going to give you the amount of iodine. And the thing that the examiner picked up was that a lot of students didn't appreciate that iodine vapor is iodine molecules. So when you look up in the data book, the relative atomic mass for iodine, it's 126.9, and to work out the molar mass for these iodine molecules, that's going to be twice that expressed in grams per mole. So 253.8 grams per mole is the molar mass of the iodine molecules. And so you're going to put the mass, which is 6.35, divided by the molar mass, you just worked it out there, and that's going to give you the amount, the number of moles. And you end up, if you do that calculation, you end up with 0.0225 moles. That's the amount of iodine molecules. So that was the first thing the examiner picked up. A lot of students didn't realize they were dealing with iodine molecules, not iodine atoms. And so they got the molar mass wrong, and they worked out the amount wrong as well. Okay, once you've got that, then you're looking to substitute into the equation PV equals nRT. And we're trying to find T. So you need to rearrange that equation to make T the subject to the equation. Just do that. So T is going to be equal, if you rearrange that, to pressure and volume of the number of moles times the gas constant, R. And we've got all the data now to plug in. We've got a pressure, yep, it's there. We've got the volume, it's there. We've got the number of moles, we calculated that, 0.025, and R we can look up in the data book. Plug all those in and we should get T. But the thing that the examiner picked up is that the students, when they're doing this, have to make sure that everything is dimensionally correct. So everything has to be in appropriate units. Now, the pressure is in pascals. That's newtons per meter squared, isn't it? And because you're dealing with SI units, newtons per meter squared here, then the volume has to be in SI units as well. So volume is in meters cubed. N, well, the SI unit for the amount is moles, we've got that already. And the gas constant is 8.31 joules per Kelvin per mole. So the only bit you've got to work on here is that the volume you've been given is in decimeters cubed, and you need the volume in meters cubed. So you've got to do a little calculation there. And you know that 1 decimeter, that's a tenth of a meter, is the same as 10 centimeters. And that's the same, isn't it, as 0.1 meters. And so when we have 1 decimeter cubed, that's the same as 1,000 centimeters cubed, and it's the same as 1 times 10 to the minus 3 meters cubed. All right, so those are the relationships there. And it means to convert a decimeter cubed into a meter cubed, then you've got to multiply by 1 times 10 to the minus 3. So you're plugging all these numbers in, making sure that you're dimensionally correct. You've got the pressure in newtons per meter squared. You've worked out the volume, it's going to be that times 1 times 10 to the minus 3. You've got the amount, the number of moles, you've got the gas constant, you plug all those in, and it comes out to give you 600 Kelvin. All right. This one is testing a little bit of your knowledge about enthalpy definitions, because you can see they're talking down here about enthalpy of combustion and enthalpy of formation. All right. And you've got basically a couple of choices there. So it's enthalpy of combustion of hydrogen. Well, is that a candidate here? Well, you need to know that the enthalpy of combustion is the enthalpy or the energy that's released when 1 mole of a substance reacts completely with oxygen. So if we had to write the enthalpy of combustion of hydrogen, it's going to be that, isn't it? You've got 1 mole completely combusted with oxygen. So that's the enthalpy of combustion of hydrogen, and then you've got the enthalpy of formation of water, and the definition of the enthalpy of formation is when 1 mole of the target compound is formed from its elements under standard conditions with all reactants and products in their standard states. So the enthalpy of formation of water is, well, hydrogen and oxygen gases making water. I'm just putting the state symbols in, you should have those in. Okay, so these equations that we've derived from these definitions are the same, aren't they here? And we're trying to find out what X is there. And you can see that our choices are, is it 4 times the enthalpy combustion of hydrogen, or is it 2 times the enthalpy of formation of water? Well, you can see here that it's actually this one, isn't it? It's the enthalpy of formation of water, 2 times that, because we're getting 2 moles of water at the end. If it was 4 times the enthalpy of combustion of hydrogen, then it would be 4 lots of hydrogen up there, 4 moles of hydrogen. So it's definitely one of these 2 here. And because we're just drawing the line in the correct direction, the arrow in the correct direction, we're forming water, then that arrow correctly represents the enthalpy of formation of water. And so we don't need to change its sign or anything like that. So that is just, that very there is 2 times the enthalpy of formation of water, which is answer D. Okay, this is an easy one, question 4. We're looking at some properties here. It tells us that we've got a giant covalent structure. And really, I mean, the ones, a very familiar giant covalent structure that you know, of course, is silicon dioxide. And that's giant covalent because actually the silicon is tetrahedrally bonded to 4 oxygen atoms, which themselves are bonded to another silicon, and the structure builds itself up like this. It's a genuinely giant covalent structure. All right? And you can see that because you've got this giant structure with all these covalent bonds linking all the atoms together, that is, of course, going to have a very high melting point and a high melting point. To be an electrical conductor, you would need to have delocalized electrons available, and there's none there, so it's going to be poor electrical conductor in the solid. To conduct electricity in the liquid, you have to have ions, and of course there's no ions in here. It's a giant covalent structure. And if you're having a solution that conducts electricity, well, then that's got to have the ions dissolved in it as well. And so there's no ions here to be dissolved. That is insoluble. So really classic giant covalent structure is silicon dioxide, and something like silicon dioxide, a giant covalently bonded substance would have high melting point, high boiling point, no delocalized electrons, no ions, and because there's no ions, it's not soluble to form an aqueous solution that conducts electricity. Okay, good. All right, so next one, we're looking at molar enthalpy change. And the trick here is that you've got this value here for specific heat capacity. Now, probably in a lot of the work that you've done, the specific heat capacity would have been related to the number of joules relative to mass and the temperature change. And so what's happened here, you need to spot, is that they've changed the way you're working with a specific heat capacity from one that's based on the mass of a solid to here the volume of a liquid. You've changed to a volume from a mass. That's just something you have to spot while you're doing that. And this is the reaction of sodium hydroxide and hydrochloric acid. You're making sodium chloride, of course, and water. And you've got, haven't you, you've got the volume of sodium hydroxide, 25 centimeters cubed. You've got the concentration of sodium hydroxide, and that was 0.35 moles per decimeter cubed. And from that, the volume and the concentration, you can work out the amount, the number of moles. And if you do that calculation, you end up with 8.75 times 10 to the minus 3 moles. And you've got a stoichiometric relationship here, 1, 1, 1, 1. All the coefficients are 1, they're implicit, they're not written. And so the amount of sodium chloride that is formed, the number of moles, is exactly the same. It's 8.75 times 10 to the minus 3 moles. Okay, now you have up here that you've mixed 25 centimeters cubed with another 25 centimeters cubed, so you've now got a total volume, haven't you, of 50 centimeters cubed. And when you did that, this neutralization reaction, the temperature rose by 2.5. We assume no heat was lost, and you've got an equation then that the heat is equal to, normally you think of the mass times the specific heat capacity times the change in temperature, but on this occasion, we're not working with mass, we're working with volume, if you remember. This specific heat capacity was written in terms of volume. So we've got the volume times the specific heat capacity, represented in its units for volume, times the temperature change. So our volume was 50 centimeters cubed, and the specific heat capacity is 4.20 joules per centimeter cubed per Kelvin, and the temperature change is 2.5 Kelvin, because 2.5 Kelvin is the same as 2.5 degrees Celsius. So you do all that, and you find that the heat that's released, assuming none was lost, is 525 joules. But that's 525 joules, isn't it, for that amount? And really we want to find the molar enthalpy change. So to find out the amount, not for 8.75 times 10 to the minus 3 mole, but for 1 mole, then you divide 5.25 divided by the amount, and that gives you 60,000 joules. And then you can just say, well, that's the number of joules for 1 mole, and it's a bit easier to express it as 60,000 kilojoules for the 1 mole per mole. Good. Okay, this one interesting. You got aluminium chloride, and in the vapor you get these dimers formed. A dimer is 2 individual molecules joined together. So this is the monomer over here, and this is the dimer. And it's saying, well, what happens if you compare the bond angles in the monomer to the bond angles in the dimer? And really, you've got to know at this point that if you drew the monomer, well, what shape is that? That's trigonal planar, isn't it? It's 1 aluminium as the central atom surrounded by 3 chlorine atoms. And so the bond angle there for trigonal planar is going to be 120 degrees. And then when you draw the dimer, you have to draw a diagram like this. Because you've got these arrows here are coordinate or dative covalent bonds, which it means that the 2 electrons in the bond both came from 1 atom originally. In this case, they're being donated by the chlorine atom. Okay. So at this point, you can see that the aluminium is now surrounded by 4 chlorine atoms in the dimer, same here. All right, and so that bond angle now is square planar. So that bond angle there is 90 degrees, isn't it? All right. So and if you go round each of these bond angles now, where you have chlorine, aluminium, chlorine, chlorine, aluminium, chlorine, wherever you go, they're all 90 degrees. So here, all the bond angles were 120 degrees. Here, all the bond angles are 90 degrees. All the bond angles have decreased. So the answer to that is C. Okay, so this is where these multiple choice questions just sort of make you do a few mental gymnastics, because you've got to select the answer here which is incorrect. And up to this point in the paper, I think we'd be selecting answers that are correct. So we're just having to sort of switch our thinking a little bit. And if you go through all of these, well, that's a correct statement. Just Le Chatelier's principle. That's a correct statement. That's a correct statement. Okay, so they're all pretty obviously correct. So this one, even if we didn't test it, we should know by inference that that's the incorrect. All right. So this is the way that you might want to try some of these multiple choice questions. You know, if you're not sure of positively identifying the answer that you want, you can negatively exclude all the things that are obviously wrong, and that leaves you, if there's only one choice, with something which must be the answer that you need. So that's we kind of did that back to front there and excluded the things that were correct, and that left only one thing which must be incorrect. So the answer there is B. But you can positively check as well, because this is an exothermic process, and if you increase the temperature for an exothermic process, then that means the position of equilibrium is going to be forced back towards the reactants. And it's said that the increasing temperature causes a higher yield of sulfur trioxide, the product. Well, that's not right. It'll give you a lower yield if you increase the temperature. Right, so this one is interesting. So you've got this reaction here, and it says which conditions would reduce the rate. So this is, isn't it? This is a question about kinetics, rates of reaction. Okay, and there was a distractor up here because it was giving us, it's telling us it was an exothermic reaction, and that's all to do with thermodynamics. But actually, so that's a distractor because it says we want to know about the kinetics that are related to this reaction here. So the information there about exothermic was really a distractor for you. So we've got a question about kinetics, and we want to keep the aluminium and the barium nitrate unchanged. So there's two things, we've got two columns. Now if we want to reduce the rate, then, well, the temperature should be going down, shouldn't it? If the temperature increases, then the rate of reaction will increase. So immediately we can see that can't be right because those are the higher temperatures, you see? And even if we're kind of guessing at this point, at least we're getting a guess out of, with a probability of getting it right of 50% rather than 25%. So we got rid of a couple of answers there, which we know must be wrong, because if we're reducing the rate by reducing the temperature, which is what we've got there. So that just leaves us to work on this bit here. And that comes to the second part of the question, where it says it wants to have the aluminium and the barium nitrate unchanged. And it says, well, will they be unchanged at pH 7 or will they be unchanged at pH 14? Well, you should know that aluminium has amphoteric behavior with acids and bases. So you can react aluminium with acids, you can react aluminium with bases. But if we want to keep aluminium unchanged, which is what it's saying here, we don't want to react it with an acid and we don't want to react it with a base. So let's have it at pH 7, a neutral pH, and so there won't be a reaction with any acid or any base. So, you know, it looks like we're zeroing in on this. You know, we certainly don't want to be at pH 14, which is a basic pH, because aluminium we need to be unchanged, and that reacts with bases. The barium nitrate part, you just need to know that, like all nitrates, barium nitrate is soluble, but barium hydroxide is actually a lot less soluble than barium nitrate. And so, for example, if we increase the pH up to pH 14, then we might start making some barium hydroxide, which is going to be possibly insoluble, depending on how much water there's around. The water's drying in this drying process anyway. So again, if we go to pH 14, some of the barium nitrate is going to become barium hydroxide, and we don't want that to happen because we're trying to keep barium nitrate unchanged. And so for both those reasons, keeping the aluminium unchanged and keeping the barium nitrate unchanged, we're choosing a neutral pH rather than a basic pH, an alkaline pH. So that means that one's out, and we're positively selecting A as our answer there. Good. Next one. This is a question about the overall dipole. And so the thing that you're working with here is distinguishing between an overall dipole and a polar bond. Okay, so the polar bond is created because you have an electronegativity difference between the two atoms in the bond. And here, what we're focusing on is the electronegativity difference between carbon and chlorine atoms means that chlorine atoms will have a slightly negative charge and the carbon atoms will have a slightly positive charge. So these are polar bonds. We've got a polar bond there, another polar bond there. You can see these are the polar bonds in each of these molecules. There they are. And there's one here, actually. It's like this, I can take that chlorine off there. It's down there. Okay. So these are all the polar bonds. And the way to derive the overall molecular polarity or the overall dipole is you have to do a little bit of vector addition. Now, this is the easiest one to see here because you've got one polar bond and its dipole going that way, haven't you? And that's an arrowhead at the end there. And then you've got the other polar bond going that way. You've got, there they are, that one there and that one there. Because these are vector quantities, that the bond has a direction and one end of it is negative and one end of it is positive, then you can do a little bit of a vector addition. And so the overall polarity is the sum of those individual bond polarities. So the overall polarity is the sum, or the vector sum, of those two individual bond polarities. So this molecule will have an overall dipole, symbol for dipole is a mu, going that way. Similarly, same kind of argument, this molecule will have an overall dipole going that way. This one here, you can see you've got one vector going that way, another vector going that way. So, you know, those two look like they're going to cancel each other out, almost actually. So that looks like it's going to have the smallest overall dipole because these two vectors are effectively cancelling each other out. And so this one as well has dipole there as well. And it could have, if this chlorine atom was over here, you could have the polar bond and its vector pointing that way. So it's not that one because that was creating quite a large overall dipole. It's not that one because that's also creating quite a large overall dipole. So you've got to choose between this A and D, and the vectors here are going to be pretty much cancelled out much more than they are over here. So D is the right answer there because the individual polar bonds are pretty much cancelling each other out because they're pointing in opposite directions there. So the smallest overall dipole for that one was D. Okay, question 10, I think fairly easy. Of course, you know that the equilibrium constant for this reaction is concentration of hydrogen iodide squared divided by the concentration of hydrogen divided by the concentration of iodine. Now they don't give you concentrations; they're giving you the number of moles, aren't they? You've got 2 moles of hydrogen, 0.3 moles of iodine. But the relationship between amount and concentration is that the concentration is the amount divided by the volume. And because this one would, these reactants are all in the same volume, so there will be a term there of V squared, and at the bottom there would be a term of V multiplied by a term of V, which is V squared. So those two V squareds would cancel out, and you can then derive and say, well, the equilibrium constant is the number of moles of hydrogen iodide squared divided by the number of moles of hydrogen times the number of moles of iodine. I2, isn't it? But we're trying to find the number of moles of hydrogen iodide. So we've got to rearrange this equation to make the number of moles of hydrogen iodide to be the subject of the equation. And if you do that, you end up with the number of moles of hydrogen iodide squared is equal to the equilibrium constant times the number of moles of hydrogen times the number of moles of iodine. And then to get the number of moles of hydrogen iodide, which is currently squared, you can then say, well, we're going to, let's rub that out, take the square root of both sides, and then you have to excuse my computer pin here. So we're going to have to do the equilibrium constant times the number of moles of hydrogen times the number of moles of iodine, and then take the square root of all of that. And if you do that, you plug all the numbers in, you end up that you have to take the square root of 36, and the square root of 36 is 6, and so the right answer there is C. Good. All right, so looking at some Boltzmann distributions here, and you should, well, to help yourselves, you could say that the temperature of Q is greater than the temperature of P, because when you raise the temperature, then the average moves to the right here, and you get a greater number of molecules over here with more energy. So Q is at the higher temperature compared to P. And over here, we've got these two activation energies, X and Y is obviously at a lower activation energy than Y. So we then have to look at the table that they've given us here, and the right answer for this one is C, because, well, the higher temperature was obviously this line here, wasn't it? The peak had shifted to the right, and there were more molecules over here with a higher energy. So clearly Q is at a higher temperature. And in the presence of a catalyst works, doesn't it, by lowering the activation energy. So the activation energy is lower for X than it is for Y. And so a catalyst would then be lowering the activation energy, and so we'd end up with a lower activation energy, which is X. So at that point, answer C is the correct one. Okay, so next one. Let's see, we've got to see which statement is correct. Well, you're talking about group 7, so you've got chlorine, you've got, in order, going down the group, you've got bromine, you've got iodine, you've got at the top of the group fluorine, haven't you? So, and you know that the reactivity of these elements increases up the group. In fact, they become stronger oxidizing agents as you go up the group. And so chlorine can oxidize bromide ions, but of course it will also oxidize iodide ions because chlorine is more oxidizing than bromide or iodide. So that's not correct. Fluorine is the strongest oxidizing agent, so well, that's not correct either. And iodide ions are the weakest reducing agent. Well, if fluorine molecules are the strongest oxidizing agent, then iodine ions are going to be the strongest reducing agent. So that's not correct either. So I suppose we've arrived at this point by saying, well, even if we don't read the question there, that must be the right answer because we've excluded the first three. But let's just, as well as negatively, identify it by excluding the answers A, B, and C. Let's try and positively identify it. Chlorine reacts with water, yep. And when it does that, it makes hydrochloric acid and that as well. And you can see here, if you write down the oxidation number of chlorine, oxidation number of chlorine there is 0, isn't it? Here, the oxidation number of chlorine is -1, because hydrogen is always +1. And here, the oxidation number of chlorine atom is +1, because the oxidation number of oxygen is usually -2. And so that means that we've properly got a disproportionation reaction where the chlorine is both oxidized and simultaneously reduced. There it's reduced, there it's oxidized. So we can positively identify that D is the right answer for that. Good. So in this question, they're putting mixing, aren't they? Calcium hydroxide, and they're mixing with barium hydroxide. And you need to know that as you go down group 2, the hydroxides become more soluble. And so barium hydroxide is more soluble than calcium hydroxide. So if in a solution of barium hydroxide, you'll have more OH minus ions than you would have an equivalent solution of calcium hydroxide. So when you mix those two together, you're going to have a precipitate forming of calcium hydroxide. And so it says up here, so the white precipitate Y forms, well, the white precipitate is calcium hydroxide, and so that must take out that, and it must take out that, which leaves us with these two at the bottom here. So the white precipitate is filtered off, that's leaving the barium hydroxide behind, and if you add carbon dioxide to the barium hydroxide that remains behind, then you're going to end up with a white precipitate of barium carbonate. So that means that one's wrong, and answer C is the one that we want. Okay, so looking at the melting point of these chlorides, well, magnesium chloride, of course, is ionic. That's going to have a high melting point, and hydrogen chloride is a gas, isn't it? So that's going to have a low melting point. So immediately we can take out this one, because magnesium chloride has got the highest melting point, which leaves these three up here. And we know that hydrogen chloride is a gas. The other two are liquids, actually. So that must mean that we can take out that one as well. We're excluding both A and we're excluding D. So we've got magnesium chloride having the highest melting point. Yep, we were good about that. And we've got hydrogen chloride having the lowest melting point. Yep, we're happy about that. So we've just got to compare then, well, which out of these two is going to have the highest melting point? Well, if you look in the periodic table, then the relative atomic mass of phosphorus is much more than the relative atomic mass of carbon. Okay, you can see that. So that's giving us a clue that actually, because this has a greater relative atomic mass, it may in fact have a higher melting point. But there's another thing you have to bear in mind as well, is that you're looking at the size of these molecules. Now, carbon tetrachloride is going to be much smaller than phosphorus pentachloride. So this is small, and this is large. This is a larger molecule, and this is the smaller molecule. And with larger molecules, you're going to have more dispersion forces between the molecules, these intermolecular forces, because the opportunity for dispersion forces to form is much greater with a larger molecule than it is with a smaller molecule. And so you'll get there, you'll have more intermolecular forces. Excuse my writing. The forces are dispersion forces or transient dipole-dipole interactions. And so that means that phosphorus pentachloride, because it has more intermolecular forces, will have a higher melting point than carbon tetrachloride. And that means that that row there, row B, is the one that we want. Phosphorus pentachloride has a higher melting point than carbon tetrachloride. Funnily enough, this next one was something that the examiner flagged up that lots and lots of students got wrong, strangely enough. So you're burning calcium. What color is the flame? This is just something you have to know, really. Well, if you did flame tests, perhaps you did those at GCSE, a flame test for copper ions gives you a green color. A flame test for sodium ions gives you a yellow color. A flame test for magnesium gives you a magnesium burns with a bright white flame. Calcium burns with a red flame. So that's calcium, that's magnesium. And the examiner said that a lot of students actually chose this by mistake because they thought these two were both in group 2. They knew magnesium had a white flame. They thought calcium would be like magnesium, and so they chose white. But calcium burns with a red flame. Okay, question 16. I think it's quite an easy question. You've got to look at aluminium oxide, and you've got to think about the bonding and the acid-base nature. Well, you know, don't you, that aluminium oxide, you can use aluminium oxide in the industrial process for extracting aluminium, which is an electrolysis. And so aluminium oxide must have quite a lot of ionic character if it's going to be used in an electrolysis to produce aluminium in the industrial process for extracting aluminium. So we know that the bonding in aluminium oxide is ionic. And that means we can scrub that one out, doesn't it? And that one out straight away. Yeah, we've got rid of those. So that just leaves us with these two choices here. And aluminium oxide is one of the classic examples of a metal oxide that is not basic, like many metal oxides, but is amphoteric. Amphoteric means that it can act both as a base, it can react both with bases and with acids. And so C is the correct answer here because aluminium oxide is ionic, yes it is, and it reacts with acids and it reacts with bases, it's amphoteric. This one always seems to come up in these Cambridge International Exam questions, talking about the thermal decomposition of group 2 nitrates. And you need to know, here's group 2, you start with beryllium, you've got magnesium, you've got calcium, you've got strontium, and you've got SR, and you've got barium, and they put up here the formula for the nitrate. Typically, you might compare magnesium nitrate and barium nitrate. And you need to know that the thermal stability increases down the group. So this is thermally stable, and this is thermally less stable. Okay, so if this one is stable and this is less stable, which one is going to require the highest temperature for its thermal decomposition? Well, the one that is more stable will need the highest temperature to decompose. And so you're looking down the group here, the one that's at the bottom of the group is barium nitrate. So you're choosing answer A there is the most stable of the group 2 nitrates, and so you're going to need a higher temperature to trigger its thermal decomposition. Okay, question 18, looking at nitrogen reacting with hydrogen to make ammonia. It's that, isn't it? Okay, so, and you've got to, they tell you, don't they? Can I just try and write that a bit more neatly for you? So you've got nitrogen, there we go, and you've got the stoichiometric coefficient is 3 lots of hydrogen, and this is the Haber process, isn't it? You're making 2 lots of ammonia, all right? And it tells you that the volume here was 2 decimeters cubed. And it tells you you're looking something up in the data booklet. The thing that you're looking up under room conditions is the molar volume, which is 24 decimeters cubed per mole. All right, and if you've got 2 decimeters cubed rather than 24, then you can work out the amount, the number of moles. So you can work out the amount, the number of moles. That's going to be 2 divided by 24, and that gives you the amount of 0.083 moles. Okay, but it tells you that actually, even though you've got that number of moles, only 15% of those moles actually reacted. So you've got to work out, haven't you, 15% of that number of moles. You've got 0.15 times that number of moles, and that gives you an answer of 0.0125 moles of nitrogen that have reacted. Looking at the stoichiometry, then for every 1 mole of nitrogen, you're getting 2 moles of ammonia. So if that number of moles of nitrogen reacted, then you'll have double the number of moles for ammonia, which is 0.025. And then you need to look up the molar mass for ammonia, which is 17 grams per mole. And then if you know the number of moles and you know the molar mass, you can work out the mass, which is the mass, which is the number of moles times the molar mass. That's 0.025 moles times 17 grams per mole. And the answer to that gives you 0.425 grams, which is answer B. Good. This is a kind of graph that you haven't seen before. You're trying to look at the relationship between electronegativity and atomic radius. And you're given silicon, aluminium, magnesium, sodium. You need to recognize, don't you, that those are all in period 3 of the periodic table. So this is a kind of periodicity question that's being asked, because those 3 elements are all in period 3. In period 3, you've got sodium in group 1, magnesium in group 2, and then you've got aluminium and you've got silicon. Those are the first 4 elements in period 3. And as you go across a period, what happens to the electronegativity? It increases. And as you go across a period, the atomic radius, well, it's getting smaller. So out of these 4, silicon will have the highest electronegativity, but the smallest atomic radius. And conversely, sodium is going to have the smallest electronegativity, but the largest atomic radius. So let's see where we can see that. Well, look over here. Silicon is there. Has it got the highest electronegativity? Yes. Has it got the smallest atomic radius? Yes. And then the sodium one was the opposite of that. It's got the lowest electronegativity and the largest atomic radius. So what we're doing is we're taking our knowledge of periodicity and just plotting an unfamiliar graph here. Silicon through aluminium, magnesium, and sodium. And so the answer B is the one that you want there. Okay, so looking at these organic reactions, this is just something you really need to know. The only thing you could spot here, actually, is that you've got ethene, haven't you? And it's having an addition reaction with bromine. And it's saying which one occurs quickly at room temperature. It's actually A, but I suppose you could go through your organic reactions and look up all the reaction conditions. But I think the thing they're looking at here is that you should know that a quick test for a carbon-carbon double bond is to add bromine water. You just do that at room temperature, bang, you do the experiment, and instantly the carbon-carbon double bond reacts with the bromine in the bromine water. So the test for unsaturation is bromine water decolorizing. It happens quickly at room temperature because it's an easy test that you want to be able to run. So this reaction, you should know, occurs quickly at room temperature, not because you've learned all the reaction conditions, or that would help, but because you know that adding bromine to a double bond is a quick test that you can easily do at room temperature. So the answer there is A. Okay, so you've got this, if I write out the full displayed formula for this chemical here, you've got, was it hydroxyethanol? So you've got that, you've got an alcohol, haven't you, at one end of the molecule, and then the other end of the molecule, you've got that. So you've got an aldehyde, so that's an alcohol, and you've got an aldehyde. And you're using acidified potassium dichromate, and that is oxidizing. And it says, look, no further oxidation takes place. So maybe there's a couple of oxidation steps that happen. And if this gets oxidized, well, the aldehyde will be oxidized to a carboxylic acid, and the alcohol will be first oxidized to an aldehyde, and then continue to be oxidized to a carboxylic acid as well. And so after you've done the oxidation, both ends of that molecule are going to be carboxylic acid. So that should be, I'm trying to draw a carbon there, didn't really come out. So carbon there, another carbon here, and that's also been oxidized to a carboxylic acid. Okay, so that's our displayed formula, and we've just got to check that with one of these skeletal formula here. Well, look carefully. In that skeletal formula, there's 1, 2, 3 carbons. Where did the third carbon come from? There's no third carbon, so that clearly isn't right. This one, you've got 1, 2 carbons. We've got a carboxylic acid there, a carboxylic acid there. That looks exactly like the displayed formula that we wrote here. In this one, the aldehyde has been oxidized, but the alcohol hasn't. And in this one, the alcohol has been oxidized, but the aldehyde hasn't. But acidified potassium dichromate will oxidize both the alcohol and the aldehyde to give you a dicarboxylic acid. Answer there is B. Okay, looking at an ester here. And an ester, of course, is a reaction between a carboxylic acid, we'll draw it like that, and an alcohol. I've just drawn R1 and R2, those are carbon chains. And let me just draw all the bonds in there. So to make an ester, you react an alcohol and a carboxylic acid. And it's an elimination reaction where water is eliminated. Can you see H2O there? And it gives you that R1 and R2. And that bond that you've got there is the ester bond. So we're trying to make this ester up here. So we've got CH3 going to that, haven't we? And then down here we've got CH2, C, CH3, CH2, CH3, and there's a hydrogen on there. Okay, so if you've got an ester like that, that must have come from a carboxylic acid there and an alcohol there. So that's come from that carboxylic acid and this alcohol. I'll draw it all out. All right, so you've got to look down here and see which of these gives you the ethanoic acid and that alcohol there. Well, that's got methanoic acid, that can't be right. these other, so that we know that's wrong, don't we? So we've got ethanoic acids there and there. That's ethanol. Remember, it's ethanoic acid we're looking for, so that one must be wrong as well. We've got rid of 2 candidates already, so it must be one of these 2 down here. And we're looking for this alcohol, which has got CH3, CH2, C with the methyl group there, CH2OH. And if you look carefully, then that is that alcohol there. It's just been turned back to front for us. But you've got that CH3, CH2 group, there it is. Then you've got the methyl group, there it is. And then you've got CH2OH, CH2OH. Excuse the fact that my computer pen's got a bit messy, but you can see that actually we've definitely got ethanoic acid, and we've got that structure there, which was that structure that we determined from the alcohol and the acid that must have reacted to make the ester. Okay, now you've got a primary that's the halogen there, and the halogen could be either chlorine as the halogen, or it could be iodine. And you've got to say, well, which one of these is going to react faster or slower in this case? So when the halogen there is chlorine, it's slow, and when it is iodine, then it's fast. And iodine has the much weaker bond. So that bond is going to break much more easily for iodine than it is for chlorine. And it's for that reason that the iodine compound reacts faster than the chlorine compound. Good. Looking at structural isomers here of C5H12. And this is quite difficult. You've got to look through these isomers and work out which ones are incorrectly written. Now, you have to look through them all, but just take this one, for example. You can't have, can you, CH2 group in brackets. Really, you've got to have a CH3 group in brackets, because if you compare those 2 there, you're writing CH3 and then CH, and then you've got the methyl group off there, and you've got CH2, CH3. So the right way to write the formula is to say, well, that's the CH3 group, there it is. Then you've got the CH group, there that is. And you've got a methyl group, which is off the main chain. The main chain is there, 1, 2, 3, 4. That's off the main chain. And so you put brackets CH3 to show that that's off the main chain. And then you're doing CH2, CH3. Okay, so that is the right way of writing the structure, the formula. That's the wrong way. So you've got to work through all of these and see that in each of these answers, there's going to be one formulae which is written incorrectly. And if you look carefully down here, for example, that formula is actually the same as that. All right? So those aren't 3 different isomers, but they're just 2. So if you like, on each of these lines, A, B, C, and D, there's something that isn't quite right. And actually the only line where everything is correct is the line C. You can draw the displayed formula, and then when you write the formula down, then the formula that's written correctly represents the displayed structure, or the displayed formula. Okay, so you've got this molecule here. I'm just going to have to get a power cable to the Mac. One moment. All right, so just fixing up some power supplies. I'll keep going, get the power supply fixed up in a moment. Okay, so you've got this compound up here, which if we write out the displayed formula, then you've got that, haven't you? And you're reacting it with cyanide ions. And the mechanism is you've got the cyanide ion there. That's slightly negative. And that's slightly positive there. The carbon is slightly positive. That's a carbon atom there. And so you've got an electrostatic force of attraction between this cyanide ion and the slightly positively charged carbon carbon center there, and so you get that mechanism, and those arrows represent the movement of a pair of electrons. Good. So what happens then is that you get an intermediate forming where you've got the negative charge on the oxygen there, and you've got the new bond that's formed there. And so that is the intermediate. And later on, because you had hydrogen cyanide, you've got some protons, and the proton can, a bond can form between the oxygen here and the proton, and so you end up with an alcohol group there. But the intermediate was oxygen with a negative charge on it. Now, look at this. So a chiral center means you've got a carbon with 4 different groups bound to it. So that's 1 different group, 2 different groups, 3 different groups, but that group is the same as that. And so there are actually only 3 different groups bonded to the central carbon, not 4. So it's not chiral. Now, in this mechanism, that was a nucleophilic addition, wasn't it? That was a nucleophile attacking the carbon there. So it's not electrophilic, it's nucleophilic. The intermediate contained an alcohol group. Well, no, it didn't. The intermediate had oxygen with a negative sign on it. Only at the end of the reaction did you get the alcohol. So the intermediate is that. So the intermediate did not have an OH group. And so just by the process of elimination, then the answer for that question is D. All right, complete combustion of 3-methyl pent-2-ene. So really all they're getting you to do here is to convert the name of an organic molecule into a molecular formula. So you've got pent. Okay, so pent is 5, isn't it? So you've got 1, 2, 3, 4, 5. So that's the stem. That must mean the longest chain is 5 carbons long. And it's pent 2-ene. So you start numbering from over here. That's 1, 2, isn't it? So that's pent 2-ene. And on the carbon number 3 is a methyl group. So you've got that there. And then the rest, of course, you've got hydrogen atoms on these other carbon atoms here. So you can now that you've looked at the name of the molecule, you've drawn the displayed formula, and from the displayed formula, you can then work out the molecular formula. And if you add all those up, you end up with C6H12 as the molecular formula for 3-methyl pent 2-ene. And then once you've got the molecular formula, it's pretty easy to say, well, your complete combustion will give you carbon dioxide and will give you water. You've got 6 carbons there, you must have 6 carbons there. You've got 12 hydrogens there, you must have 6 lots of water molecules to give you 12 hydrogens. And so to balance that all up, you will need 9 moles of oxygen. And so your answer to that is 26A. Good. Talking about reducing the chain length of hydrocarbons from fractional distillation through a process of cracking. And the thing that you need to remember about cracking is that you've got these long chain hydrocarbons, and cracking generally gives you small alkenes. So you might get ethene, for example, or you might get propene. These are a typical product of cracking is to make small alkenes. All right. Now, if you look here, that's only 1 carbon shorter than the original hydrocarbon. So in cracking, of course, we're trying to reduce the carbon length by 2 or by 3 because we want to make these short chain alkenes. But here we've just reduced the carbon chain length by 1. So that is very unlikely to be produced in a cracking reaction because you're trying to produce a 2 carbon or a 3 carbon alkene from the parent long chain hydrocarbon over there. And here we've just knocked off 1 carbon atom, which can never be an alkene. So that's most unlikely or the least likely to produce in the cracking reaction. Okay, so we've got a molecule up here. It's got an unbranched carbon chain. It's got 2 alcohol groups. And when we oxidize it, then we end up with this. And you can see the oxidation has given us 4 oxygens. Well, that must mean that the original carbon chain had a primary alcohol at the end of each chain. Because when you oxidize it, when you properly oxidize a primary alcohol, you end up with, don't you, a carboxylic acid. I'm not drawing in all the hydrogens. And that's the way that you get the 4 oxygens. You've got a dicarboxylic acid. If this was, in fact, something like this, where you had a primary alcohol there, and what's that? That's a secondary alcohol. When that's oxidized, then the alcohol, the primary alcohol, would become a carboxylic acid, but the secondary alcohol could only be converted to a ketone. And there you've got 1, 2, 3 oxygens, and we're told up here we have 4 oxygens. And so we must be making a dicarboxylic acid from a long chain here with a primary alcohol at each end. And so the answer there is C, that one there. Now 29 was one the examiner flagged up that hardly any students got right. In fact, the examiner said that less than 10% of students actually got this question right. And there's a trap waiting for you, really, because it's looking at this compound here, which has 2 double bonds, and it's talking about geometrical cis-trans isomers. Now, the thing is that you could have, the easiest way to explain this is by drawing the skeletal formula. So that's actually, if you think about it, that is a cis isomer. Yeah? Now, you can see the number of potential permutations would be, well, you could have cis and trans, couldn't you? We'll write them in a moment. Or you could have trans and trans. Or you could have, the final possible permutation is trans and cis. And if you draw out all the skeletal formulae, what you find is, well, let's do them. So this is cis trans. This is trans-trans. So that's cis-trans. So that's cis-cis. That's cis-trans. That's trans-trans. And then the last one, this one here, trans-cis, is going to be like this. Okay, all right. So, you're just thinking here where you've got 2 possible isomers, you've got 2 double bonds. It looks like you should be answering 4 over here. There's 4 possible isomers because you've got cis-cis, cis-trans, trans-trans, and trans-cis. But the examiner is trying to get you to spot that actually this shape, I call that number 4, you've got 1, 2, 3, and 4, actually 2 and 4 are actually the same thing. If you can just imagine, you could swap that one around or turn it around a bit, and it would actually fit exactly against that. So actually, although it looks like there should be 4 possible permutations, actually cis-trans and trans-cis actually are exactly the same molecule. So that's a tough question, and most people got it wrong, but the answer there is C. Okay, so the thing to spot here is look at these stems. So that's prop, so that means 3 carbons, and the result at the end is but, so that's 4 carbons. So immediately we can see by looking at the names of these compounds that we're extending the carbon chain by 1 carbon. We're going from a prop stem to a but stem. And so that must mean that we need to use the cyanide to extend the carbon chain. There's no way the carbon chain can be extended by using those reagents, and there's no way the carbon chain can be extended using those reagents. So immediately, those are out of the question, and we've reduced the difficulty of this question down to a choice between A and B. And you just need to look up your reaction mechanisms, and actually you're using that, and the answer to there is A. Right, so we get into a rather more complex part of the paper now, where instead of just choosing one answer, we're getting the choice to choose either 1, 2, and 3, 1 and 2, 2 and 3, 1. So we've got some different ways of doing multiple choice here. So we're going to be using the data booklet, and we're talking about N2F4, and when you heat that, it decomposes to only one thing. And the most natural way of thinking about that is that you've got a dinitrogen tetrafluoride molecule, you've got N2F4, and when you heat it, that's essentially a dimer, and that's going to be forming 2 lots of N2F2 because it decomposes, doesn't it, into only one product. There's only one thing that's being formed there. All right. So if you look at that, the bond that's being broken is the bond between the 2 nitrogen atoms. So are any nitrogen-fluorine bonds broken? No, they're not. So that isn't correct at all. Then if you look up in the data book, it tells you that the average bond enthalpy for a nitrogen to nitrogen bond is actually plus 160 kilojoules per mole. So that you just look up in the data booklet, you know no nitrogen fluoride bonds are breaking, it's a nitrogen-nitrogen bond that's breaking, and the data booklet has the value 160 for that. And then you just need to do a quick check that, well, do you think that molecule is going to be non-linear? Well, one way to think about this is with a quick dot cross diagram. Nitrogen has 5 valence electrons, fluorine has 7. That means there's going to be 2 lots of fluorine, there's 14 valence electrons. There's 19 electrons to go into our dot cross diagram. So we're running out of space here. We're going to have nitrogen in the middle, going to have fluorine, fluorine. We've got to have at least 1 bond pair of electrons because the nitrogen is joined to both fluorines. We can add the rest of the electrons to complete the octet around the fluorine. So we've got 8, 8. We need to use, what was it, 19 electrons. So we can start putting those on the nitrogen atom. It's actually a radical molecule. It's got an unpaired electron, but they're not looking for that in this question here. But and then you can see that you've got these electron domains around the nitrogen. So you've got a nitrogen, and you've got a lone pair of electrons, and you've got another electron domain there, and then you've got the bond pair, and you've got the bond pair there, and so you're going to have a stronger force of repulsion between the bond pair and the lone pair, between the bond pair and the bond pair. And so that ends up with being a bent molecule rather than a linear molecule. So it's true that these molecules are non-linear. So that's correct as well, which gives us answer 2 and answer 3 are both correct. And that gives us, against the key up here, answer C. Okay, so P and Q, they have similar relative molecular masses, but P has hydrogen bonds and Q doesn't. It just has van der Waals forces. And so let's look at some of these then. Well, if P has got hydrogen bonds are stronger than van der Waals forces, so P should actually have a higher melting point than Q. So that's not right, is it? And anything with hydrogen bonds is highly soluble in water because the molecule itself can form new hydrogen bonds with the water molecules. So we would expect P to be more soluble in water than Q. So that's not right. So by a process of elimination, it looks like that one is right, and we just have to understand a little bit about surface tension. And the idea there is that if this is a liquid, that's the surface, and this is the bulk of the liquid down here. And if you've got a molecule of P, then it can have hydrogen bonds all around it. You can have hydrogen bonds bonding it to the left, to the right, below it, and above it. So it's got hydrogen bonds in all 3 dimensions around it. But at the surface, you've got hydrogen bonds pulling down, hydrogen bonds to the side, hydrogen bonds to the other side, but no hydrogen bonds at the top. And so you end up with a net force of pulling the water molecule on the surface down. And it's that overall force from the unbalanced hydrogen bonds that leads to surface tension. And so when you've got stronger bonds pulling P down, that gives you a higher surface tension than Q. So the answer there is 1 only, and 1 only gives us answer D on the multiple choice key. All right, these two are reacting together. This is a question about kinetics, isn't it? Because it's asking us about the rate of the reaction. So we're answering a kinetics question here. Okay, that's just the kind of information that we're getting from the question. And we know that activation energy has an effect on the rate of the reaction. So if the activation energy is lower, the rate is faster. So that is a factor that will affect the rate of reaction. The enthalpy change, well, that's a thermodynamic property. So that's not related to rates of reaction at all. It's a thermodynamic property. So that doesn't affect the rate of reaction. And the equilibrium constant is just something that you determine experimentally. It's nothing to do with a factor that affects the rate of reaction. You know that the factors that affect the rate of reaction are things like concentration, things like surface area, things like temperature, or having a low activation energy. These are all things that affect the rate of reaction. The equilibrium constant doesn't affect the rate of reaction at all. And so you've just got one again there, and that in the answer key is an answer D. Okay, Bronsted and Lowry bases here. Talking about a Bronsted and Lowry base, and a Bronsted and Lowry base, if you remember, is a proton acceptor. So we've got to look through here and through these here and work out which ones are proton acceptors. You can see here in for this one here, HSO4 is actually accepting a proton from water, so that is a proton acceptor. And the nitric acid is actually accepting a proton here, isn't it? Well, there it is. It's accepted a proton there. So it's accepted a proton from sulfuric acid, so that is a proton acceptor. And here, that nitrogen, that ion, is just reacting with water. It's not accepting a proton, it's reacting with water. So that's not right. So you've got 1 and 2 there, and that, according to the answer key, is B, isn't it? So when you've got 1 and 2, the answer key is B. Pollutant here. So the actual answer to this is, the pollutant contains the non-metal element, so X, nitrogen is X, and the oxide is nitrogen monoxide. So that's the whole molecule is nitrogen monoxide. We can just check that against these statements here, because when you react that in the atmosphere, so plus a half oxygen molecule gives you NO2. So the oxidation number there is changing by a factor of 2, so that's correct. If you draw out that molecule there, it generally has an unpaired electron in the molecule. You'd have to do a Lewis diagram here, so that's N has 5 electrons, oxygen has 6 valence electrons, you've got 11 valence electrons to distribute around the molecule. Clearly, if you've got some bond pairs and lone pairs, that's not an even number. You're going to end up with an unpaired electron in the molecule. So that's true. And it's a polar molecule, is that right? Because you've got nitrogen and oxygen, you've got an electronegativity difference between them, and so you're going to end up with one molecule being slightly negative compared to the other end of the molecule, which is slightly positive, because there's an electronegativity difference between the nitrogen and the oxygen. So in this case, all of those are correct. And when you've got 1, 2, and 3 correct, that gives you answer A. This is looking at the thermal decomposition of hydrogen halides. So you've got the iodide is going to be going to that. I should 2 there. And the bromide is going to that. And the answers here are that and that, because at a low temperature, this doesn't happen at all, and at a higher temperature, both of those reactions are happening. And you don't have a temperature where one reaction happens and the other doesn't happen. Okay, talking about redox reactions here, you've got to spot that that is a ketone, and Tollens reagent is a test, isn't it? Not for ketones, but for aldehydes specifically. So there's no reaction here at all, and if there's no reaction, it can't be a redox reaction, can it? Here you've got Fehling's reagent, which is again a test for aldehydes. And there, it's true, this time you have got an aldehyde. So there will be a reaction there. So that was no reaction there, can't be a redox reaction. That is a reaction, and that is a redox reaction. And this is a redox reaction as well, because when you end up with the addition product, the bromine has gone from an oxidation number of 0 to an oxidation number of -1. So when you have 2 and 3 together, that gives you answer C, doesn't it? Okay, they're giving us the answer key again. Okay, we're looking at esters again. And you've got this, haven't you? Right. So that's true, that is ethyl butanoate. So that's correct. And if you work out the molecular formula of that and the molecular formula of hexanoic acid, they're identical. So that's correct as well. And then it's talking about the last step here, hydrolysis. And the hydrolysis would be breaking the bond here, and that would give you ethanol and butanoic acid. And they've got it the wrong way around. They've got butanol and ethanoic acid, or sodium ethanoate. So that's not correct there. So the answers here is 1 and 2. You've got answer C. Almost done. Okay. You've got pentan 1-diol. That's I'm not drawing in the hydrogen atoms. You've got the alcohol group at each end. You've got a primary alcohol there, haven't you? And a primary alcohol over here. Okay, so you need to know that when any alcohol reacts with sodium, it's going to give you the ethanoate, sorry, the sodium salt there, plus hydrogen. And stoichiometry there is 2 lots of that, 2 lots of that, 2 lots of that, 1 mole of hydrogen. So you can see when you react an alcohol with an acid that 2 alcohol groups give you 1 mole of hydrogen, which is correct here because you've got 2 alcohol groups giving you 1 mole of hydrogen. So that's correct. You've got this question here. So that's correct, isn't it? Okay, so if you oxidize this, you can end up with an aldehyde, can't you? Because you're just reacting that there, or maybe reacting that one there. So an oxidation product of this possibly is an aldehyde, and the 2,4-dinitrile phenyl hydrazine reagent can be used to detect an aldehyde. And then finally, so that's correct. This one is correct as well, because if you take that formula there, you've got a C4, H. So what am I talking about? Sorry, I've gone wrong in this question. Sorry. have to rewind and have another go at this one. Okay, so what was I doing? This is, the stem there is pentan. What was I thinking? So that means 5 carbons, isn't it, in a chain? 2, 3, 4, 5. And it's a diol. So there's a primary alcohol here. That's a carbon 1, 2, 3, 4. And you've got an alcohol here. And so that's, you've got a primary alcohol there, and you've got a secondary alcohol there. All right, so that's, so the discussion we had about the stoichiometry still holds. We've got 2 alcohol molecules. Now, if we do a oxidation here, then that primary alcohol there, when it's fully oxidized, is going to be a carboxylic acid. But when this secondary alcohol is oxidized, that's going to be a ketone. So that's where I went wrong, isn't it? So the 2 oxidation products, either a carboxylic acid or a ketone, and it's the ketone that reacts with a 2,4-dinitrophenyl hydrazine reagent. That's a thing that you can use to characterize a reagent. You can use to characterize ketones. And the molecular formula of this is C5H12O2. If you dehydrate that, you're losing water twice. You're losing 2 lots of water, and that gives you C5H8. If you just subtract those 2, you end up with this formula here. So it ends up as a compound with an empirical formula C5H8, which is correct. So 1, 2, and 3 are all correct. Look at that up in the answer key. Gives you answer A. Last question here. And this is one of the ones that the examiner flagged up that students had difficulty with, strangely enough. There we go, okay. So really, all you have to do is you have to spot that butan-2-ol, butan-1-ol, and 2-methylpropanol, they all have a molar mass of 74 grams per mole. So that means you've got 1 mole of that, 1 mole of that, 1 mole of that, and in principle, they should give 1 mole of that, 1 mole of that, and 1 mole of that. And so you work out the molar mass of each of these and see then if the molar mass multiplied by 62% is giving you the actual yield that you got. So for example, the molar mass of butanedione is 72 grams per mole. So 1 mole of butanediol should give 72 grams of butanone. But because you've only got a 62% yield, you've got to multiply that by 0.62, and 0.62 times 72 gives you that. And if you do the same kind of calculation for butanoic acid, and you do the same kind of calculation for 2-methylpropanoic acid, then you get that value and that value. All those conversions are consistent with the information in the question. So 1, 2, and 3 are all correct. That is the answer A. Good, all right, so well, that was the AS level chemistry, the paper from 2014. I hope you've enjoyed walking through that with me today. If there's any more questions, then all the Z coaches are going to be on the Slack channel, and you're very welcome to join that Slack channel and talk with the Z coaches any more about the questions that we've been through as we've gone through the paper today. So I wish you every success with your chemistry studies and look forward to the next paper that we go through. Okay, bye-bye.